So we're going to introduce the kinetic energy work theorem, which is really handy at different times, and is especially handy when we're dealing with friction. Okay, so this is lesson 5 in our unit on momentum and energy, and to begin, we'll say that when we know that when a force is applied to an object over a certain distance, the velocity of that object changes. Right? We've seen it in real life. We've seen it in the physics classroom. And we know it's true because work is being done on the object. So really, if work is the transfer of energy, then basically we're transferring energy to an object, and that results in some kind of motion happening to that object, right? So let's take a look at this mathematically. And if we start with the most basic definitions, we've got work is equal to force times displacement, and we've got F equals ma. So this comes from Newton, and here's our energy topics, and we're going to collide them now. And what we can say is that then work is equal to, and instead of writing force, we write ma, dotted with displacement. Okay? So this would be the net force that's acting on some object, right? The overall sum of all the forces combined acting on the object. But hey, wait a second. Let's go back to kinematics, and let's remember our first two most basic equations for kinematics, really the only two that we need, v2 minus v1 over time, and v1 plus v2 times time, and of course it's an average, so we take the half. And we're going to sub those in to this equation. So instead of writing a, we write this, and instead of writing d, we write this. We'll see that time cancels out. We get a time up top, we get a time down below. We get this little factor of a half in here. And then we get these two terms, v2 minus v1 and v2 plus v1. Well, it's very interesting. What is that? v2 minus v1 times v2 plus v1. That, ladies and gentlemen, is a difference of squares. And we can exploit the fact that it's a difference of squares to write it in a little bit of a different way. And so what we'll do is we'll say, oh yeah, we can write it like this. 1/2 m v2 minus v1, v2 squared minus v1 squared. And if we separate that out, we get, hey, look, the sum of all the work that we do on an object, right? So all the different ways that we can apply work, if we add up what all those different works are, that gives us a change in our velocity. It actually gives us a change in our kinetic energy. And this is the work-kinetic energy theorem. Okay? So here's the equation. Work is equal to the change in kinetic energy. And all we need to do is we just need to remember, okay, well, what was kinetic energy? Well, you should have seen it down there. 1/2 mv squared is, of course, kinetic energy. And so what we can do is we can start to use this. How much work in megajoules is required for a cargo jet of mass 4.55 times 10 to the 5th kilograms to increase its velocity in level flight from 105 meters per second to 185 meters per second. Well, what do we know? We know mass, we know v1, we know v2. We can find out the change in kinetic energy. And if we can find out the change in kinetic energy, that's how much work is required. So here it is. Work equals the change in kinetic energy. We can write this as 1/2 mv2 squared minus 1/2 mv1 squared. And say, okay, let's simplify and substitute and solve. And we get 5,278 megajoules of work required to change this object's velocity from 105 to 185. Okay, let's go in a different direction. Let's look in 3 dimensions. 3 dimensions. And we'd say we get a 2 kilogram mass and it's got this velocity. What's its kinetic energy? So, how do we handle v squared when we've got 3 dimensions? How would we handle v squared if we had 2 dimensions? What is v squared? It's v times v, or more accurately, v dot v. So kinetic energy is 1/2 mv squared. But we can actually write this as the dot product between two velocities. And it's going to give us the same thing. So if we ever receive a vector that's in I hat and j hat direction and we want to calculate v squared, we just take the dot product of it with itself. And in this case, this has just got this little k hat term floating around here. The dot product looks exactly the same. 2i hat minus 3j hat plus 6k hat dot 2i hat minus 3j hat plus 6k hat. And how do we do the dot product? 2 times 2 plus 3 times 3 plus 6 times 6. And of course, the 1/2 and the 2, they just go away. We get 49 joules. So the kinetic energy of a 2 kilogram mass with this velocity, 49 joules. We can also look at kinetic energy and momentum because we'd be remiss if we didn't. Kinetic energy has an mv in it. Momentum has an mv in it. So maybe we can express kinetic energy in terms of momentum and vice versa. Let's square momentum. We get m squared and v squared. Okay. Next, well, let's divide both sides by m. So we get p squared over m equals mv squared. Hey, we're almost there. Let's multiply both sides by 1/2. So we get 1/2 p squared over m equals 1/2 mv squared. Hey, look, we got kinetic energy. And we've successfully expressed momentum in terms of kinetic energy. P squared over 2m equals ek. Okay? Now, we can write this another way. We can express momentum in terms of kinetic energy or the other way around. So this is valid, but it means the same thing as this. This is the way you most often see it, but not always. Let's use this in an example. Determine the momentum and speed of a proton that has a kinetic energy of 4,280 electron volts. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. All right. Well, we should note at the beginning that an electron volt is a unit of energy, and 1 electron volt is equivalent to 1.602 times 10 to the minus 19 joules. So we can convert this. We know that our kinetic energy is 4,280 electron volts, which in terms of joules is quite small. 6.848 times 10 to the minus 16 joules. Okay. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. So we want to determine the momentum of this proton. So we're going to use momentum equals root 2m times the kinetic energy. And here it is, a substitution. And once we solve it, we get 1.51 times 10 to the minus 21 kilograms. We can then use this result for momentum to find out the speed that it's traveling at, because velocity is equal to momentum divided by mass. And here we can do this little calculation, and we find that the speed of our proton is 9.06 times 10 to the 5th meters per second. So that was lots of fun with momentum and energy. We looked at the work-kinetic energy theorem. We're ready to go on to something a little bit different. We're going to talk about potential energy in the next lesson.